you to define the damping matrix, assuming a damping ratio of 5% for the first and the second mode of vibration, and to compute what will be the damping ratio for the third mode of vibration. This is what you will have to do anytime you will be using sub 2000 ETABS among or similar for a linear analysis, meaning you will have to define the equivalent damping ratio for two modes of vibration. You will have to compute the equivalent damping ratio for all the other modes of vibration. And you will have to verify if that equivalent damping ratio that you are getting for all the other modes of vibration is realistic or not. If it's not, well, clearly you need to change your assumptions. So again, you define the equivalent damping ratio for two modes of vibration because you have two equations, and you compute what is the equivalent damping ratio for all the other modes of vibration to then verify if the value that you are getting is realistic or not. The characteristics of the system are given on the slide. You will find a problem which is very similar to this one as part of the final, okay? So everything is given here. The modes of vibration are given, the periods of vibration, the frequencies of vibration are given as well. Now, the first thing that you need to do is to write the mass matrix and the stiffness matrix. You need to do that because all you're trying to do is to say that the damping matrix C is a combination of the mass matrix plus the stiffness matrix. The combination is written here, A0 times the mass matrix plus A1 times the stiffness matrix. What you want to do now is to obtain the two constants of A0 and A1. The equations that you need to use are written here. So all you need to do is to plug in the values for the two frequencies you have selected and for the equivalent damping ratio to find A0 and A1. Now, you can simply write the damping matrix as a combination of these two. When it comes to computing the equivalent viscous damping for the third frequency of vibration in this case, what you need to do is to remember that the equivalent viscous damping is obtained using this formula or can be obtained using this formula. If now you plug in the values of A0 and A1 which you obtained, you will be able to find the equivalent viscous damping, which is 6% in this specific case. Guys, questions regarding, in reality, classical damping is very easy, as I mentioned at the beginning. The reasoning is very easy because we are able to write the mass matrix and the stiffness matrix in a diagonal way. Well, it's clear that if I write the damping matrix as a combination of these two, I will be able to write a diagonal matrix. All the different formulations which we have seen and the implication of this formula are clear, okay? So before I move forward, do you have questions regarding, classical damping? Anybody? Let me ask you, is it clear? Anybody? Alan?
Yeah, just in regards to that example, since you're looking for the damping for the first and second mode, you'd be using the first and second frequencies in finding the coefficient?
Yes.
Okay.
So in this example, clearly, you need to, when using this formula, you need to define two values of damping, two values of frequency, omega I and omega j, for which you want to fix the value of equivalent viscous damping, which in this case, for this problem, is set to be 5%. So the problem is telling you, look, find the Rayleigh damping matrix such that the damping ratio is 5% for the first and also for the second mode of vibration. Then find what is damping, the equivalent viscous damping for the third mode of vibration. So you are setting the equivalent viscous damping as 5% for the first and for the second mode, the problem is asking you what is the equivalent viscous damping for the third mode of vibration or for the frequency of the third mode of vibration. Because you have two equations for A0 and A1, which are written here, you will be setting up the frequencies of mode 1 and mode 2 in this equation to obtain A0 and A1. Then, here you will be writing the frequency of the third mode of vibration, A0 and A1 were obtained before, to obtain what is the equivalent viscous damping for the third mode of vibration, which is larger than 5%. Okay, is larger than 5%. In this problem, is roughly 6%. Why 6%? Well, because you have defined 5% for these two frequencies, 5% for these two frequencies. Then you know that damping is increasing roughly linearly. Therefore, if the frequency is larger, you will find a larger value of damping. Okay? So this is the theory behind it. Another way to model Kogai damping, or to model damping, is called the Kogai damping. Even in this case, the damping matrix is written as a combination of the mass matrix and the stiffness matrix. The formula is written here. Okay? So even using another form of damping, this damping is called the Kogai damping. The conclusion is that the damping matrix is written as a combination of the mass matrix and the stiffness matrix. Again, you need to perform this operation because if you know how to decouple the mass matrix and the stiffness matrix, then the damping matrix will be as well a diagonal matrix. So this is the reason behind using a combination of the mass matrix and the stiffness matrix. Well, because the damping matrix can be written in this way, you can find that the equivalent viscous damping for all the frequencies in the system can be written using this equation. Now, clearly, in this equation, you will define for how many modes of the n degree of freedom system you want, if you wish, use the series. So for how many modes of the n degree of freedom system you want to define the equivalent viscous damping. So in the following slide, an example is given. So imagine that in your multi-degree of freedom system, using the previous formula, you are defining the equivalent viscous damping for only 3 modes of vibration. So you were able to find omega 1, omega 2, and omega 3. You go back to the previous formula, use the previous formula only for omega 1, omega 2, and omega 3. Okay? And from this formula, you find the constants which are needed as before. You find the constants which are needed to obtain a value of, say, 2% of the equivalent viscous damping across these 3 frequencies. Well, the problem is showing you that clearly if you use only 3 modes, and if you plot the frequency across the equivalent viscous damping across all modes of vibration, this is the result that you get. So the damping will be the one that you assigned for the 3 frequencies, but then it's going to decrease. If you assign the equivalent viscous damping for the same problem that we have seen, but for 4 frequencies instead of 3, then clearly you have assigned the damping for these 4 frequencies. So for this frequency, for this frequency, for this frequency, for this frequency, you have defined a value of damping of, say, 5%, but then past this frequency, damping will be increasing. Okay? So when using Kogai damping in one of the software we have been mentioning, Well, the formula behind Fourier damping is written here. This is the combination that you will be using to write the damping matrix. If this is the combination, the equivalent viscous damping for each mode of vibration will be given by this formula. If the equivalent viscous damping is plotted across all the modes of vibration, if it's plotted across all the modes of vibration, then you will see that clearly it's going to be the value that you define for the specific frequency, but then it's going to change. Those software will be plotting for you this diagram, okay? Those software will be plotting this diagram for you. So it's important that you check that the value of damping that you are obtaining for frequencies that you are not selecting is still modeling the structure with a good approximation. Meaning, for instance, for frequency for the seventh mode of vibration, you don't want to end up with a value of damping which is too large and not realistic, okay? Because otherwise, the results that you will be obtaining from your analysis will be wrong. Guys, do you have questions regarding, how to model damping in your structures? Well, clearly, this classical damping can be used only when the system which is dissipating energy in your structure is constant, meaning when the mechanism which is dissipating energy in your system is always the same. So for instance, if you need to model the interaction of a foundation and of a structure, and if you want to model damping for this system, well, because you have systems with a very different amount of damping, so for instance, the foundation will have a damping of say 20% of critical, the structure will have a damping of only 5% of critical, then clearly damping is very much different in the two systems. Well, in this case, you cannot use classical damping. You cannot write damping as a combination of the stiffness matrix and of the mass matrix, but what you need to do is to assemble the damping matrix. Well, in this case, meaning you need to write a damping matrix which is modeling the structure and the damping matrix which is there to represent what's happening at the soil, and this damping matrix must be written, meaning it cannot be assumed as a combination of the stiffness matrix and the mass matrix. This is called the non-classical damping, meaning every time the damping matrix must be written, cannot be written as a combination of the mass matrix and the stiffness matrix. You're talking of non-classical damping, Well, in most of the problems you will be working on, you will be using a classical damping. You will be using one of the options we have seen before, and the problems which are assigned at the end of this presentation will cover basically those concepts, okay? So for instance, in this problem, the properties of a 3-degree of freedom system are given, and the problem is asking you to derive the relay damping matrix such that the damping ratio is 5% for the first and the third mode, and compute the damping ratio for the second mode. This is very much the problem that we have seen before. In problem 2, instead, the problem is asking you to find the damping matrix for the system of problem 1 by superimposing the damping matrices for the first and the third mode, each with a damping of 5%. Verify that the resulting damping matrix gives no damping in the second mode of vibration. For both problems, you will need to use the formula that we have seen before. So this is all regarding today's presentation. I mean, it's a very simple topic. The conclusion of the story is the following. To decouple, so conclusion, wrapping up in 1 minute. conclusion is the following. The scope of a modal analysis is that of decoupling the equation of motion. You start from a system of equations, you end up with n equations, each of which is representing a single degree of freedom system. This is only possible because the stiffness matrix and the mass matrix can be written as diagonal matrix. When I find the generalized mass Mn, when I find the generalized stiffness Kn, these matrices can be written as diagonal matrix. Because I cannot, play with my problem and write diagonal matrices, well, clearly, if I write the damping matrix as a combination of these two, then clearly I will be able to decouple the equation of motion. If damping is written in this way, then we are talking about classical damping. Specifically, in this case, we call it relay damping. If damping is written as a combination of the mass matrix and the stiffness matrix, well, clearly the implication is that I will not have a constant damping across all the frequencies in my structure. I cannot obtain a constant damping across all the frequencies of my structure. Damping will be changing. The best I can do is to define damping for two frequencies. Because I have two equations, I can only define damping for two frequencies. I can plot what is the value of equivalent viscous damping for all the other frequencies in my system, and I can verify that my assumption is modeling with a sufficient level of accuracy the reality or not. Okay? If this is not the case, clearly I need to change my assumptions. Okay, this is all for today. Again, it's a very quick and easy presentation. Next time we will meet, we will talk about distributed mass and stiffness. Regarding the very last topic, which is distributed mass and stiffness, in all honesty, I don't think I will be including that topic as part of the final exam. And this is to give you extra time to prepare. Most of this is based on the fact that, I see that for some of you, well, I don't know, but I want to give you more time to prepare. So how to prepare for the final? Go over all the assignments. You will find something which is very similar to the assignment, meaning, super similar to the assignment. So go over the homework one more time, try to study them one more time, because you will find something which is very similar to the homework, okay? I want to make sure that if I give you something which is very similar, you will do well. So this is why I will be doing it. So, what I will do is to go over the homework and I will assign you something which is very similar, because I want to make sure that you do well. Meaning, I don't want to, if you wish, close my eyes when I grade your work. Therefore, I will give you something which is very similar to the assignment. Okay, guys, this is all for today. Do you have questions? Anybody? Okay. Therefore, bye to all. Have a good evening. We will be meeting one more time to discuss distributed stiffness and mass, and then we will be done with the semester. Thank you to all of you who decided to share a comment with me. It seems that the main comment is that you would like to see more problems, and that can be easily implemented in the future. Meaning, there are plenty of problems to choose from. Okay, so this is all for today, and again, I will see you next week. Bye, guys.
Have a good night.
Thank you. And you. Bye.